All right, I've got a couple of things I wanted to talk to you about today. Primarily, there's some stuff in the news that is both really interesting and also something that happens all the time. I don't know why this has gotten so much news uh, just this just right now, except that it happens to be on the anniversary of a giant asteroid impact, or I should say meteorite impact in Russia about a year ago. But if you've been paying attention to the news, you've probably been hearing about this asteroid that's about twice the size of a football field, that's coming within 8 lunar radii of the Earth. It flew by this morning. It missed us, thank goodness, so we don't have to worry about that. That's all true. It was flying at about 27,000 miles per hour. What's kind of more interesting, though, is that this stuff happens all the time. So if you go to a website called spaceweather.com, you'll find interesting information about space weather. Here's the huge asteroid hype. This did happen this morning, but this is happening all the time. And in fact, if you go to the Near Earth Object Close Approaches website, which you can just do a Google search for, you'll see that, as of right now, here are all of the close approaches that are currently happening this month. So you can see that, yeah, the one that went by this morning was pretty close at 8.8 lunar distances, but there was one back on the 10th that was 6.2 lunar distances, and it was roughly the same size, if not a little bit larger than the one that went by this morning. The only thing I can think of is that about a year or so ago, we had a meteorite impact the atmosphere over Russia, and if you haven't seen that video, I thought I'd go ahead and show it real quick because it's pretty amazing. So let's watch this.
What exploded over Russia? Presented by Science at NASA. When the sun rose over Russia's Ural Mountains on Friday, February 15th, many residents of nearby Chelyabinsk already knew that a space rock was coming. Later that day, an asteroid named 2012 DA14 would pass by Earth only 17,200 miles above Indonesia. There was no danger of a collision, NASA assured the public. Maybe that's why, when the morning sky lit up with a second sun and a shockwave shattered windows in hundreds of buildings around Chelyabinsk, only a few people picking themselves off the ground figured it out right away. This was not a crashing plane or a rocket attack. It was a meteor strike, the most powerful since the Tunguska event of 1908, says Bill Cook of NASA's Meteoroid Environment Office. In a one-in-a-million coincidence that still has NASA experts shaking their heads, a small asteroid completely unrelated to 2012 DA14 struck Earth only hours before the publicized event. These are rare events, and it is incredible to see them happening on the same day, says Paul Chodas of NASA's Near-Earth Object Program at JPL. Researchers have since pieced together what happened. The most telling information came from a network of infrasound sensors operated by the Comprehensive Test Ban Treaty Organization. Their purpose is to monitor nuclear explosions. Infrasound is a type of very low-frequency sound wave that only elephants, homing pigeons, and a few other animals can hear. It turns out that meteors entering Earth's atmosphere cause ripples of infrasound to spread through the air of our planet. By analyzing infrasound records, it is possible to learn how long a meteor was in the air, which direction it traveled, and how much energy it unleashed. The Russian meteor's infrasound signal was detected by multiple stations, including one in Alaska more than 6,500 kilometers from Chelyabinsk. Western Ontario professor of physics Peter Brown analyzed the data. The asteroid was about 17 meters in diameter and weighed approximately 10,000 metric tons, he reports. It struck Earth's atmosphere at 40,000 miles per hour and broke apart about 12 to 15 miles above Earth's surface. The energy of the resulting explosion exceeded 470 kilotons of TNT. For comparison, the first atomic bombs produced only 15 to 20 kilotons. Based on the trajectory of the fireball, analysts have also plotted its orbit. It originally came from the asteroid belt, about 2.5 times farther from the Sun than Earth, says Cook. Comparing the orbit of the Russian meteor to that of 2012 DA14, NASA orbit analysts have shown that there is no connection between the two. These are independent objects, Cook says. The fact that they reached Earth on the same day, one just a little closer than the other, appears to be a complete coincidence. Infrasound records confirm that the meteor entered the atmosphere at a shallow angle of about 20 degrees and lasted more than 30 seconds before it exploded. The loud report, which was heard and felt for hundreds of miles, marked the beginning of a scientific scavenger hunt. Thousands of fragments of the meteor are now scattered across the Ural countryside, and a small fraction have already been found. Preliminary reports, mainly communicated through the media, suggest that the asteroid was made mostly of stone with a bit of iron. In other words, a typical asteroid from beyond the orbit of Mars, says Cook. There are millions more just like it. And that is something to think about as the cleanup in Chelyabinsk continues. For more news about things coming out of the blue, visit science.nasa.gov.
And that's kind of the problem with with meteorites and asteroids. It's always the ones you don't see that are going to get you. It's pretty amazing when you think about it, because we had known that the other asteroid that didn't hit us was going to come by. We'd been monitoring it for a long time, and then one came and blindsided us from the backside. It's pretty remarkable that those happen on the same day. You can take a look at all this debris in our solar system, the stuff that's flying around. If you go into Celestia, if you wanted to see what these orbits of these objects look like, you can turn on, under the display feature, I can turn on a bunch of different types of objects. And I'm going to turn on what we call dwarf planets. Dwarf planets are things that are technically not planets because they aren't big enough to be spherical, but they still orbit the sun. And if I turn on those orbits, you can see this is Ceres over here. This is one of the dwarf planets. However, if I turn on the regular asteroids, this is what they look like, and I can zoom around and show you in 3 dimensions what these look like. So all of these red lines represent the orbits of asteroids, and as you can see, they pretty much fill the space between Jupiter and Mars. But they're on these really elliptical orbits, so it's not uncommon for them to come in all the way to the Earth, and you can see that several of these have Earth-crossing orbits. So that's one of the problems that we have to worry about here on the Earth with debris. One of NASA's big projects is to try and monitor all of this debris and make sure that we know when it's coming. And we have about 90% of them cataloged, but of course there's plenty that we don't have cataloged. And then of course the ones that we can't catalog are the things called comets. Now the comets originate from much further away from us than the asteroid belt. And if I turn on those orbits, you can see a distinct difference between the asteroids and the comets. These yellow lines are comets, and they tend to be on these plunging, hugely elliptical orbits. And if you look at where they originate out in the outer solar system. So you can see these orange orbits flying around here. They originate in the outer solar system, and so we really can't predict when they're going to come more than a few years in advance. So if one of the comets decides to plunge into the Earth's orbit and smash into the Earth, we're doomed. Just something to think about as you get ready for your day. At least we didn't get destroyed by an asteroid this morning, although the chances of it happening are pretty slim. It has happened in the past. Okay, any questions about that or what we've been doing so far? Today I wanted to finish up with the moons of Jupiter and the other outer planets, and that'll lay the groundwork for our next bit, which is moving on to discussing the stars in general. So I'm going to go back and show this picture that we had before of the Jovian moons, and talk about how they're a little bit different from the typical rocky worlds that we have in our inner solar system, and also talk about how excited astrobiologists are to study them as potential abodes for life. They have some pretty interesting environments. So let's take a look at Jupiter's moons first. Jupiter has a slew of moons. Some of them are quite large, and some of them are more like asteroids, small objects. If we look at the Jupiter's largest moons up here, we're just going to focus on the very largest moons for right now. And this is just comparing these to all the other planets. You'll see that Jupiter has the largest moons. There's Io here, Europa, Ganymede, and Callisto. These are often called the Galilean moons because Galileo was the first person to look up in his telescope and see these things. It's not surprising that Jupiter might have the largest moons of the outer planets because it's also the largest planet of the outer planets, and so there was more material to form stars or to form moons around Jupiter because of the gravitational influence of the large mass of Jupiter. Compare that to Saturn, where there's really only one large moon, That's Titan right here, and we'll talk about that a little bit later. Uranus and Neptune have some relatively small moons compared to those. And then just to put this into perspective, here at the bottom is Mercury, our moon, and Pluto. So you can see that if we had Ganymede, for example, orbiting the sun, it would be a planet. It definitely falls into that category. It's large enough to be circular. The only reason we don't call it a planet is because it's orbiting Jupiter instead of orbiting the sun by itself. The same with Europa and Io. They're definitely large enough. Titan's large enough. So these are planets in their own right. If they had had the happenstance to be formed orbiting just the sun, we'd call them planets. So there's really not much distinction except they happen to form around a giant planet as it was forming. Again, the way that these large moons they do have to be large enough to be spherical. They have to have enough gravity so that they, over their formation time, they're hauled together by gravity primarily. That's in contrast to something like an asteroid, which is held together by chemistry, and it looks like a little potato. There's not enough gravity to really haul it into a ball. Almost all of these moons, in fact, all of the ones I'm showing here, have a substantial amount of ice, and they all formed in orbit around giant planets. These tend to circulate all in the same direction, so we think that they formed around Jupiter almost like a mini solar system. So just like Jupiter and Saturn and Uranus formed around the Sun out of a solar nebula, the moons of Jupiter must have formed around a little nebula of material around that core that was forming Jupiter. So they really are sort of mini solar systems compared to the other debris in the solar system. The small moons, on the other hand, are almost too numerous to count. They tend to be captured asteroids or leftover comets or other sorts of junk and debris. And the main thing that singles them out is they look like asteroids. They're just little chunks of rock. And so these are either material that never formed into a moon or a planet, or material that got blasted apart from a moon or a planet. And they're everywhere. I mean, they tend to circulate around Jupiter and Saturn because there's so much mass there. But there really are, if you hear something like Jupiter has 22 moons, well, those are the ones we've found. There's probably countless more. That number changes all the time. As far as the large moons, though, there's just the ones that we've seen. Okay, so let's take a look at Io, Europa, Ganymede, and Callisto. These are the 4 Galilean moons, and you can see that as we go on this side, this is the closest moon. This is Io, that's closest. So imagine Jupiter is over here, and if we go out from Io, this is the order of the planets: Io, Europa, Ganymede, and Callisto. And these moons are incredibly geologically active. You can see that the closer in you go, the more geologically active they are. And the reason I know that is basically the number of craters on the surface. If you imagine all of those meteorites and asteroids and stuff flying around in the solar system, the surfaces of the planets are going to record the impacts that occur over time. So if you have a planet that has a surface with very few impact craters, it's constantly being resurfaced by geological activity. If you have something with more surface craters, it's not quite as geologically active. So if we look at Io, we don't see any craters at all. In fact, all the craters we do see are really volcanoes. Then we look at Europa. Again, there's a couple little craters on Europa, but not a lot. Europa is covered by these cracks, but there aren't a lot of craters. Then you move out to Ganymede. Ganymede has even more craters. Still shows these little cracks and things like that, but for the most part there are a lot more craters. And then there's Callisto, which has a lot more craters than even Ganymede does. So clearly whatever is happening geologically is occurring because these things are closer in to Jupiter. So that gives us a strong hint as to what's causing the geological activity. The geological activity has to be caused by proximity to Jupiter, therefore it has to be caused by the gravitational influence of Jupiter, and in particular it has to do with the gravitational tidal influence that's kneading these planets as they orbit the planet Mars, or the planet Jupiter. The volcanic activity on Io is the largest in the solar system. Even though our planet is very geologically active, Io is so geologically active that it's just resurfacing itself all of the time. It would be a very interesting place to live because as soon as we take a picture of one of these geological areas, it changes as soon as we come back and take another picture. So the differences, though, is between the geological activity on Earth and on Io is that Earth's geological activity tends to be molten rock, molten basalt. Io's geological activity tends to be sulfur-based, and there's an awful lot more water ice and things like that. Just to put this in perspective, because it's pretty amazing, the geological activity on Mars or on Io causes these enormous volcanoes, and here's an example of one of those volcanoes right here. This volcano is covering, the outgas from this volcano is covering something like a fifth of the surface of the planet or something crazy like that. There's very low surface gravity because Io is so small, so when you get an eruption, the material just blasts off and lands a large distance away from the crater. So you can see that these volcanoes are amazing events on the surface of Io. Now let's move to Europa. Europa is also geologically active, again because there are so few craters, but it has a much different character. It doesn't have a lot of volcanoes. It has these surface cracks and surface breaks that we see on the surface of Europa. Now this is a composite image of Europa in both the visible and the infrared, and it brings out these cracks. And if you look at these cracks here, you can see that they kind of crisscross the surface. These cracks are caused again by the gravitational influence of Jupiter, causing this planet to be compressed due to the tidal influence of Jupiter. And these cracks are allowing material to well up from the interior of Europa. So it's one of the things that indicates that there's a subsurface ocean underneath the crust of Europa. Another thing that indicates some sort of subsurface ocean is if we zoom in on the surface of Europa. So that what we're doing is we're looking at one of these features, close up right here. Let's zoom in on that feature, and you can see that these cracks go all the way down to the finest scale. This scale bar down here is what, 5 kilometers? Do you have a question, Shay?
No.
Okay, so this is 5 kilometers here. Can't really read that, so I'll write that in. 5 kilometers. This is 2 kilometers. So these are, put Weber State Campus would be right here. Weber State Campus would be right here. Give you some perspective. These cracks go down to the smallest area, and in fact you can even see that these cracks kind of line up. You could put these things together like a jigsaw puzzle. You can see that there's this crack here that probably lines up with this crack here, and there's a little piece material here that looks like it broke off from over here, and you can even see areas where there's a deeper shadow, which means that the area that's tilted in this direction. This big block of ice is tilted in this direction, and so what you're seeing are areas of Europa where the surface is broken up and refrozen. And it looks very similar to how you might imagine the surface of a icy planet would look like if it had water under the surface and somehow you broke up the surface and it refroze. So again, this is another indicator that we think that there's some sort of subsurface ocean underneath Europa's surface. If that's the case, this subsurface ocean is enormous. It's probably the largest liquid water ocean in the solar system. And I say that because even though Europa is relatively small, Europa's not much larger than the size of our moon, this water layer has to be deep. And so the water layer here that they're illustrating is looking like, from the top of the ice all the way to the bottom, you're looking at something like, 100 kilometers. Now, if you think about our planet, our ocean is only on average about 3 kilometers depth. So 3 kilometers, our ocean would be something like right here. So you're looking at something that has a lot of volume because it's very deep. This ice up here could be relatively thin. It could be 100 meters thick, a kilometer thick. It could be 10 kilometers thick, right? We don't know how thick the ice is because we haven't managed to drill through it or anything. But if you imagine worst case scenario, you've got 10 kilometers of ice, 100 kilometers of ocean. If there are things like volcanic activity at the bottom of this ocean, you have a huge volume of water that wouldn't be too dissimilar from what we have on the oceans of our planet underneath the surface. Again, if you take into account the surface gravity, since this planet is so small, the surface gravity is less, so you can be you can be in a lot more water and still have reasonable pressures. Now, to give you some perspective as to how difficult it would be to explore this, we have drilled down in Antarctica something like of order 10 kilometers. So we haven't gone quite that deep, but the drilling technology, if we sent a drilling rig to Europa, we could probably drill through the surface given enough time. I don't think that would be a problem. However, the problem is living on the surface of Europa for an extended period of time is really hazardous. Not only is it cold and there's no atmosphere and all that kind of stuff, but it's orbiting through Jupiter's massive magnetic fields, and that motion creates a radiation environment that would kill you as a human being in a few hours, and it would fry electronics in a matter of days. So how do we operate in that environment? That's the tricky part. We'd have to have some kind of shielding, and there would be a bunch of engineering constraints that we'd have to deal with. So it's a very difficult environment to work in, but it's tantalizing because it's this huge liquid water ocean. Now, just recently, over this past year, they've discovered geysers shooting out of some of these regions. So imagine having a little geyser shooting out like this. What that means is that there's some crack that has a pathway down to the surface, or underneath the surface to the water. If that's the case, that makes it a lot easier to take samples, because you can send a very low flyby orbiter to just zip through the plume of the geyser and have a collection device that scoops up some of the material shooting out of the geyser and then fly back to Earth for analysis. So there is some possibility that we'll be able to analyze the contents of this ocean without having to drill all the way through it, which makes it a lot cheaper of a mission to do. So Europa is one of the coolest places we would like to go with NASA, and I think it's something that we were talking about building a Europa lander, and we're talking about doing some kind of sample return, although the discovery of these geysers may change a little bit of that. But within the next decade or so, I imagine you'll see some kind of mission to go to this moon and explore this liquid water ocean. Now, if we go out from Jupiter, we get further away from the gravitational influence of Jupiter, and the gravitational tidal heating goes down, and Europa turns into a planet or moon like Ganymede. Ganymede has, again, you see some of these cracks, but they're not nearly as frequent or intense as Europa. And if there is a liquid water ocean under here, it's got to be very deep inside of this moon, and because we just don't see the same type of cracking that we see. We see some grooves, and we see evidence of, that the surface is flowing and moving, but we don't see the same sort of upwelling or glaciers or anything like that, icebergs, that sort of stuff. Plus, we also see a lot more impact craters. So I think that Ganymede, whether or not there's a liquid water ocean on it, there could be, but it's going to be much deeper and much more difficult to access. So Europa is really the target for all this stuff. And then as we get out to Callisto, Callisto is effectively like the Mercury of the Jupiter system. It doesn't have much geological activity at the surface. It's almost entirely crater pockmarked with craters. One thing interesting about Callisto is it does have a magnetic field, and that's interesting because usually that's reserved for objects that have a molten core. On the other hand, it could be a induced magnetic field from Jupiter, which is still interesting because it says something about the properties of the core of Callisto. So Callisto would be an interesting place to study, not so much for life, but just because it's another example of a solid rocky or solid object that's different than our rocky planets, but has some similar characteristics. So it would be interesting to study from that perspective. Okay, so that's the Jupiter moons. If we move out to Saturn, there's one place I want to talk about, and that is the moon of Titan, or the moon of Saturn called Titan. Titan is interesting because it's about the same size as our moon, and it illustrates the point that if you were to take our moon and move it further out so that the temperature went down, it could hold on to an atmosphere. Titan has an atmosphere made out of nitrogen that's about 1.5 times what we experience here, so about 50% larger pressure at the surface than what we have on the Earth, even though it's only the size of the moon. So it's almost as if you were to take the Earth and move it out to Saturn, and that's the experiment of Titan, to see what would happen to a planet like that. So this picture is just showing the thick atmosphere here. You can see the layers of the atmosphere. The first thing that strikes us about Titan is that it's covered with this haze, and we'll talk about that in just a minute. But that haze makes it very difficult to see the surface. So one of the things that we'd like to do is get down to the surface of Titan and see what's going on. And the reason for that is because the temperature and pressure at the surface of Titan are such that there are some other molecules that will act as liquids at the surface. And so it has one of the few other environments, in fact it's the only other environment other than the Earth, where you can have a fluidological cycle at the surface. Now the fluid isn't water, the fluid is either methane or ethane or something like that, but it does stay fluid on the surface, and it forms clouds and it rains and all that kind of stuff. So again, Titan is an interesting place to see because it has this triple point fluid cycle, but it's happening at 80 degrees Kelvin instead of 273 Kelvin like our Earth. Now we did send a probe to Titan. This was back in 2006, and this probe was launched we have an orbiting probe called Cassini, which orbits Saturn, and then we had this little probe called Huygens, which we launched off of the side, and it went down to the surface to land on the surface. And these pictures that I'm going to show you are pictures of that probe landing. Titan, again, is not a very pleasant place to operate. It's about the temperature is about the temperature of liquid nitrogen almost, which means it's incredibly cold. Electronics don't last very long, and so we only have a couple of pictures from the surface of Titan. So the first picture I want to show you is this one, which is from the lander. Imagine, so this lander's coming down, so it deploys a parachute, and imagine you're on a parachute looking down between your feet. This is what you would see. There's a large ocean, not of water, but of liquid ethane and methane, which covers near the North Pole here, and we are landing right at this spot here. Now the first thing you'll notice as you're coming down here, again, this is 5 kilometers scale bar, which means Weber State Campus looks like that. And the first thing you'll notice are these little snake looking things which have all these feeders that come in, and they look for all the world like rivers, right? In fact, there's even little deltas coming into this lake of fluid. So you can see that there's liquid on the surface. It's flowing. It's been flowing for a long time because we have all these river channels, and it looks like if you were coming down in the West Desert and you saw the mountains into the Great Salt Lake. The picture that I'm showing now is the one that has the probe landing on the surface of Titan, and what we're seeing is we're looking at this plane of the surface of Titan, and one of the things that strikes us when we first look at it is it looks just like sitting out in the mud flats of the West Desert, and there are all these rounded rocks, and these rounded rocks are really exciting because every other planet we've ever landed on, all the rocks are angular. You know, they look like they've been blasted with impacts or maybe eroded by wind or something, but they aren't rounded. And the thing about these rounded rocks is that means that there has to be rain, because the only way you can get rounded rocks sitting on a mud flat is if you're raining down from the surface. So what that means is whatever this fluid is that's flowing into this mud flat is also forming clouds and raining out. And so we have this weather cycle, and we don't see this anywhere else in the solar system except for on the Earth. On the Earth we have water ice that melts to water, that evaporates into vapor, forms clouds, and rains down. On Titan we have the exact same thing happening, except it's not water, it's got to be methane or ethane. Really just gasoline. It's like you imagine having, liquefied gas on the surface. Now there's no oxygen in the atmosphere, so it's not going to explode, that's fine, but it does represent a completely different environment where a lot of the same physics are happening. The reason this is interesting from an astrobiological perspective is that a lot of people will say that, we need water because it's a good medium for life, that it's a good way to get nutrients around and to do the sorts of chemistry that we know life can do. Well, here you have a planet that has a mobile medium. It's not water, it's methane or ethane, but it's got the same physical properties. It goes through the same phases and it has the same physical states. And so one of the questions is, can Titan support life? And if it does, can it support a different type of life than what we find here on Earth? Could there be microbes up there that live in methane or live in ethane because that's the dominant medium to mix stuff around. And we don't know the answer to that question, but it's someplace we'd like to go and find out. And it does represent an interesting case study. If there is no life up there, then that's very telling because that means that makes it more likely that there is something special about water that's important for life. So Titan's a pretty interesting place from that perspective. Now, if we move on to some of the other moons of Saturn, I'm just showing this because there's two other interesting moons. One is called Enceladus, which is right here in the middle, and it also has geysers. So there's been some discussion about going to Enceladus to look for material. If you imagine geysers coming out of these cracks here, and you have the probe, you can fly the probe in orbit around it and pick up that material. Enceladus has some geysers that would be interesting, again indicating a subsurface ocean of some kind. And then the other thing I want to point out, and this is just for fun, is that there's a moon of Saturn called Mimas, and it looks just like the Death Star from Star Wars. It's got this little Death Star here, which is completely coincidental but interesting because it was discovered after Star Wars was made. So George Lucas did not see Mimas and say, oh, that looks like a cool space station. He made this cool space station, and then we just happened to find a moon that has this giant asteroid impact on it, which looks like the Death Star. But there are a bunch of other moons of Saturn which people have been studying for various reasons, but those are just a couple that are of note. One of the moons of Uranus, I just wanted to point out one of them because they show you how complex this process of formation can be. There's a moon called Miranda, which has this giant check mark on the side of it. I don't know if you can see this here, but it's got this giant check mark on the side in the middle of this big block, and it's got some other areas where it's got these big blocks, and it almost looks like, it looks like a piece of clay where you took two different colors of clay and you just mashed them together real quick and left them alone. That's much different from what we see in other moons and planets. Is in other moons and planets we see a process where material falls in and it differentiates, so you have an iron core and you have a crust and a mantle and things like that, but this almost looks like somebody just smashed it together. So clearly there was something about this process that made it a little bit more chaotic and hectic than some of the other processes we see. These moons can be great examples of, every single time we form a moon, we do it by some process, and if we can understand how all these processes work, we can get an idea of the full spectrum of possibilities. There's one other moon I want to talk about, which is Neptune's moon. Now we're out further, we're out past, we're out past Jupiter and Saturn. We're looking at these other moons, and there's a moon of Neptune called Triton, and Triton has this interesting characteristic. When it comes closer to the sun, it has jets and streaks that come off of it. It also has wind streaks and things like this where you're having outgassing of material, and then that material is depositing out on the surface. So again, you're seeing some geological evidence that when the surface is heated by the sun, and I shouldn't say closer to the sun, I should say when the surface is heated by the sun, we get evidence of some sort of change in the state of the material at the surface. And so again, this would be an interesting place to study because the question is, how much does that change impact the surface, and what does that tell us about the subsurface? So again, it's an ice ball orbiting further out there. Once again, an example of some of the strange worlds that are out there in the outer solar system. Okay, so we want to talk a little bit about why these icy moons are more geologically active than the small rocky planets, because if you think about if you think about Mercury and planets like that, they are small and pretty much dead. Now we've talked about the geological heating, but there's a few other things we have to mention about this. If we look at a comparison between rocky planets and icy moons, rocky planets are made out of different stuff. They're made out of iron, they're made out of nickel, silicon, and things like that. And so they tend to melt at much higher temperatures. So what that means is in order to get geological activity on a rocky planet, you have to have a lot more energy input. Now compare that to the icy moons. The icy moons are made out of ice. They're made out of water, methane, carbon dioxide, ammonia. Those materials melt at a much lower temperature, so you can have a lot more impact for a smaller amount of heating. So something like tidal heating can melt the ice and drive geological activity. Now, the reason I bring this up is because we're just on the cusp of finding moons around giant planets in other solar systems. And the interesting thing about that is some of these giant planets that we're finding in other solar systems are closer to the central star. Now, if they're closer to the central star, that means you can have the more condensable materials are going to be things like nickel and iron. And one of the questions is, what are the compositions of the moons of these planets around, or these moons around planets around other stars? Are they icy or are they rocky? And that's going to determine whether or not they have geological tidal heating and what their surfaces will be like. So this question about a comparison of rocky planets and icy moons used to be kind of academic, as just well, let's look at physical processes. But now we're beginning to find systems where you could imagine having a rocky Mars around a Jupiter mass planet orbiting close to the star. And we may find some of those types of systems soon, and when we do, we'll have to ask the question, what's the densities and what are the materials that they're made out of? So I just want to take us over to our syllabus, because we're making a transition now from the outer planets and the moons to studying the stars. So if you look at where we are here, today is when we talked about moons and debris in the solar system. On Thursday, we're going to talk about measuring the stars. And the very first thing we're going to do is determine, how do we know the distances to the stars? That's going to lead into your activity for next week. Now, I moved it from Thursday to Tuesday, so you have some time after we talk about it to get it done. But we're going to talk about parallax, which is the way that we determine distances to the nearby stars. After we do that, we'll talk about spectroscopy. And this activity on spectroscopy, I realized looking over it, it has a lot of specialized equipment that I usually use in class. There's a few parts of it that we're going to talk about, so I'll go over those on Tuesday. But you're not going to turn in the stellar spectra activity for credit, because there's just too much of it that you won't have the equipment that you need to do. So we'll discuss it in the discussion, but we won't. You won't have to hand that in. So you can just focus on the parallax one for handing in next Tuesday, and then we'll worry about the stellar spectra when we talk about spectroscopy on that same day.